laryngitis, and this is the best I can do. I am so sorry. I'm going to try to teach this once because I don't think I have the voice to teach it 5 times today. So today we're talking about sampling distributions, and you need to have this basic idea in your head. Here we go. So I have a very small class of 5 students. Here are their test scores: 60, 70, 80, 90, 100. I'm going to plot those on a number line, and I'm going to find the mean. Notice that their mean score is 80. And since this is a population, that means the mean mu is 80. Now, I'm going to arbitrarily pick a sample of size 3 from that population. So I randomly chose 60, 70, 80. Those I plotted on my number line. This is my sample distribution. These numbers have a mean of 70 because this is a sample. This is x bar equals 70. If I was to go through and find all possible samples of size 3, all of them, every single one of them, these are all the different ways I could pick a size 3 sample from those 5 students. Here are all their possibilities. I'm going to plant each of these x bars on the number line. So notice my number line has an x bar now instead of an x. So these all together have a mean of 80. But it isn't the mean of x anymore. It's the mean of x bar. This is called a sampling distribution. So a sampling distribution is basically like this. We start with a statistic. A statistic is a value calculated from a sample, like x bar, p hat, and s. So sample mean, sample proportion, sample standard deviation. A parameter is a value calculated from a population. So we've got mu, that would be the population mean. We have p, which is the population proportion. And we have sigma, which is the population standard deviation. What happens in a sampling distribution is that this is going to show the statistic for all possible samples of size n from that population. So a sampling distribution for a statistic is all the possible values of the statistics. Like if you were to take every possible sample and calculate that statistic and plot that statistic over and over and over again, much like we did for the Beyonce sampling problem in class. Now, what we notice is that a statistic can be simulated by actually, taking samples like we did with our dice the other day or with the Beyonce problem. And what we find out of this is this really cool thing, that the mean of the population, that true parameter, is equal to the mean of all the sample means. Okay, so I'm going to go back up here. The true mean of the population was 80. And when I took one sample, I didn't get 80. But if I take all possible samples and find their mean, the mean of all the sample means is the true mean. All right, so it's really important that we use correct language on this. We want to make sure if you're talking about a population mean, you say population mean. And if you're talking about a population standard deviation, you say population standard deviation. If you're talking about a sample, you say sample mean. So when we're using these statistics, we're going to use these to estimate a parameter. X bar is going to be used to estimate mu. So we'll find X bar over and over and over again to find mu. And S is used to simulate sigma. And P hat is used for the proportion. So we want to know about the population. So what we do is we take a random selection to get a sample. We use that to make a statistic like X bar or P hat. And then we make an inference to guess about what the true population parameter actually is. So I have this example, and I'm going to bring up this applet. Okay, so you may have heard of the Gettysburg Address, right? We've heard of this before. So with the Gettysburg Address, there are 268 words in that. If I wanted to talk about how many words there were in that Gettysburg Address and how many letters per word they are, it looks like this. It is a skewed right distribution. The mean is 4.295 and the standard deviation is 2.119. That is going to be mu and that is sigma, mu and sigma. because those are the population. Now, if I was to take a sample from that population, so I'm going to take one sample of, say, size 50. I'm going to draw the sample. Here's my words. This is my sample distribution. Okay, so the sample, notice it looks kind of like the population. It still looks a little skewed, right? You can see which bars these all came from over here. It has a mean of 4.5 and a standard deviation of 2.4. Its sample size is 50. Those are going to be X bar and S. Now, notice over here, it says statistic. That means down here I have the sample bar. So see this 4.58? Here's the dot for 4.58. So this is one X bar. So if I draw a new sample, it's going to repeatedly plot those X bars. Now, what you're noticing is that these X bars are kind of building up, just like with the Beyonce poster. I'm going to make a whole bunch of these samples now. I'm going to take 100 samples. Okay, so if I take 100 different samples, what I can notice is that this really interesting thing is happening over here at the X bar distribution. The sample distribution is changing dramatically, but if you've noticed, this X bar distribution, this sampling distribution, is staying the same shape. It is starting to look approximately normal. Notice its mean is 4.295 and its standard deviation is 0.27. So the standard deviation is still not very good, but that mean is spot on. All right, so what we notice then is that, so here's my population data. Here was the mean mu, the standard deviation sigma, sample size, the population size, capital N, is 268. That's the number of words in the entire speech. If I draw samples from this population, so I take a population is skewed right. I take a sample. Here's my sample. Notice it still looks skewed right. The sample tends to give you like the flavor of the population. It's not going to be exactly the same, but it's going to have a similar mean and a similar shape and a similar standard deviation. Okay, so this is X bar and S and N. All right, so what we have is I take the mean of this sample, which was 4.2, that's that X bar, and I'm going to plot it. There it is, right there. And I'm going to do this over and over and over again. This gives me the sampling distribution. So this is not just the mean mu. This is the mean of a whole bunch of X bars. So we're going to call it the mean of X bar, mu of X bar. This one is 4.297. You can see that that's really close to the true mean. The standard deviation is also a little better as well. All right, so the sampling distribution has a mean that is very close when it's simulated, or exactly the same if you were able to get all possible samples of that population mean, and it has a much smaller standard deviation than your sample does. Notice the standard deviation 0.270 versus 2 point something. So the standard deviation is much smaller, but the mean is very good. So here's this idea. Okay, I have this other applet. Here's what we start to notice. Let me bring this other one up. All right, so I have a population here, and this population is approximately normal. See it? Approximately normal. It's beautiful. Okay, so on your notes paper, I want you to write approximately normal right here. And so what I see is that if I was to take a sample and calculate the mean, okay, I want to take a sample of size 2. There's my 2. It drops the mean right there. And I was to do this over and over and over again, taking a sample of size 2, finding the mean, and so down here, here's this mean. If I was to do that a bunch of times, like 10,000 times, notice that this is also approximately normal. The mean is really, really close to the true mean, but the standard deviation is much smaller. This goes from 5 to 3.5 on the standard deviation, but the mean is 16 to 16. Now, if I was to also do this for, say, size 5, so I'm going to make this a little bigger. And again, I'm going to take a sample. So here's 1, 2, it drops the mean. 1, 2, 3, 4, 5, and drops the mean down there. If I was to do this over and over and over again, what you'll start to see, here I'll even do 10,000, is that both of these, I keep taking these repeated samples and finding their means, samples of size 2 and samples of size 5. The mean of the sampling distribution is the same as the mean of the population, but the standard deviation is smaller. Let me go ahead and do a couple others. Here's a sample of size 16, and here is a sample of size 25. And again, what this would look like is if I took a sample of size 15, here are my little dots. This one takes a while. And my sample of size 25, you can see what I have here, okay? So these are my means, my sample means. So I'm going to do this over and over. I'm going to take 100,000. And what you notice is, first off, these again look approximately normal. The mean is still 16, just like the population, but the standard deviation has gotten much smaller. So if I'm talking about a sample of size 2 versus a sample of size 5, the sampling distribution for size 2 is going to have a much wider standard deviation than the sample of size 25, but the means are going to stay the same. All right, so what we notice is that if it's approximately normal population, the shape of a size 2 sampling distribution will have the same mean but a smaller standard deviation. And if we go up to size 25, we also have the same mean, but we have a much, much smaller standard deviation. Now, there are a couple other non-normal shapes. Here's what we notice. So I have these other ones. So we have a skewed right, we have a uniform, and we have a bimodal. So I'm going to change this. Here is the skewed right graph. Now again, I'm going to have the mean of 2 and the mean of 25. And so if I animate here, here's that sample mean. It takes a sample of size 2, finds the mean. It takes a sample of size 25, finds the mean. 25 takes forever. All right, so you'll notice this works very similar. If I take 10,000 samples over and over and over again, I've got all these samples. Notice that the distribution of means for size 2 is still skewed to the right, but the mean of this is 8.08 and then 8.10, 8.08. The mean is still the same all the way down. And if I get 25, notice it starts to look approximately normal. If I change this and I have a uniform population, it's the same all the way across, and I find a mean of size 2, I find a mean of size 25, and I find those sample means, and then I do this over and over and over and over again. What I'm going to notice here is that the mean for both of these, the mean of the sampling distribution of size 2 is the same, and the mean of the sampling distribution of size 25 is the same, but the shape is not. First off, the sampling distribution for size 2 up here doesn't look skewed to the right. It looks like this weird triangle business, but the one for 25 looks approximately normal. And I'm going to go up here and I'm going to change this, and I'm going to make it one that is bimodal. All right, so this is a bimodal graph here. Get some bimodality. All right, so here I have this bimodal graph that I have created. All right, I'm going to take samples of size 2 and samples of size 25. Now, when I take samples of size 2, what I'm going to see is this incredible weirdness right here. Notice we have a peak at the bottom. That's what would happen if you got 2 low numbers. And we have a peak at the side. That's what you have. You got 2 high numbers. If you got a high and a low, you'd get this peak in the middle. So it's this weird, totally weird shape. Standard deviation is huge, but the mean went from 16.46 to 16.47. The mean is still spot on. The standard deviation is smaller. We went from 12 down to 8, but it is still not the same. Okay, but notice by the time we get to 25 that it looks approximately normal. All right, so here's the deal. Here's what's going on. If you have a non-normal shape of your population, your sample distribution will look similar to your sample of your population shape. But your sampling distribution, where you're repeatedly taking samples over and finding the mean and plotting them, they don't look the same. So if you have a sampling distribution for size 2, the skewed right one looked skewed right with the same mean and a smaller standard deviation. The uniform one looked non-normal. It was just like that weird triangle. But it still had the same mean and a smaller standard deviation. And the bimodal one also looked non-normal. I mean, it looked weird, right? It didn't have a definable shape. It had the same mean and it had a smaller standard deviation. But by the time we got to 25, every single one of these sampling distributions looked approximately normal with a much, much smaller standard deviation. All right, so when we have something with sampling distributions for sample means, when the population is approximately normal, your sampling distribution shape is also going to be approximately normal. And when the population is not normal, the sampling distribution will look approximately normal for a sufficiently large N. How large of an N? Depends on how bad the first one is. Usually by the time you get to about 30, you're probably pretty good. This is called the central limit theorem. If your population is non-normal, then your sampling distribution is going to look non-normal unless you have a sufficiently large N. So if you have a smaller N, it's not going to look normal. All right, so there are, here's this idea. So we're talking about sampling distribution, X bar, X bar, X bar. In a sampling distribution, the mean of the sampling distribution, the mean of X bar, will be the same as the mean of the population. That's cool. But the standard deviation gets smaller and smaller and smaller. As the sample size goes up, the standard deviation goes down. It gets a skinnier graph. And also, we notice that the shape will become more approximately normal. So as your sample size goes up, the shape of the sampling distribution becomes less non-normal and more approximately normal. All right, so here's the idea. I have this example. It says, according to the National Center for Health, the distribution of heights for 16-year-old females is approximately normal with a mean of 64 and a standard deviation of 2.5 inches. At the right, here is a statistical software that was used to generate 250 different simple random samples of size 20. From a population that would look like this. So what we have here is a simulation, basically saying if the mean is 64 and the standard deviation is 2.5, and you took 250 simple random samples, here's what X bar would look like. So it says there's one dot at 62.4. What does this mean? All right, so there's that 62.4. That means that one sample of size 20 had a sample mean height, an X bar of 62.4. So each one of these dots represents one sample of size 20 and what its statistic was, X bar. It says, would it be surprising to get a sample mean of 64.7 or more if the mean is 64? So if I got 64.7, so I counted here, there's about 17 dots out of about 250 dots. That's about a 6.8% chance of happening. So if the mean is 64, like they said, 64, like we're claiming, the chance of getting an average height of 64.7 has about a 7% chance. That's pretty good. Okay, so I mean, 7-point chance that could probably happen. So that's not unusual. So that wouldn't surprise me. I'm not surprised by that answer. But if you said, what about getting 65.3 inches? Now, 65.3 inches or more, that's only a 0.012% chance. This would surprise me. So if I found out that our average height at Avon, for example, was 65.3, then I would assume that we would be taller than the general population, because this population, 64, says if it's 64, it would be really unusual to get this result. Okay, so we're looking for that unusual. Now, there's just one more thing I got to talk about before I completely lose my voice. We've talked about bias before in taking samples. Bias, by definition, looks like this. The mean of whatever statistic you have looks like the parameter. An unbiased statistic is when your data piles up on top of your truth here. Okay, so this is like when we did the Beyonce problem for X bar. And we took random samples. If you don't take random samples, you could introduce bias and create something. This looks like bias right here. We don't like this at all. So bias, by definition, is when you take the mean of your statistic and it gives you something other than the parameter. Now, the sample statistic is we call this a point estimator of our population parameter. What we want to look for is we want to look for something ideally that gives us a close on that bullseye, that truth, but also has small standard deviation for accuracy. So this one right here, we hit this spot really close, but that's the wrong answer. So it has high bias because it's not in the right spot. It's not the right number. It's not predicting the right place, but it does have low variability, which is good. This one has low bias. If you see, it's centering on the bullseye, but it has high variability, which means even though we're close to that answer, it's not very good. Okay, so it's not a very good answer here. And then because it's on the bullseye, but it's got this wide variability. This one has high bias and high variability. I don't like this one at all. This one is the one we want. We want to center on the bullseye and have small standard deviation. So if I was going to rank these, I would put this one number 1 because I'm hitting the bullseye on average and I'm pretty close to it. I have small standard deviation, small variability. This one over here, this is number 2 because even though it has a lot of variability, it is on average in the right spot. These two over here, both terrible. I would say this would be number 3, except for it doesn't predict the right number, so it doesn't do us any good. All right, so right here it's asking if you had these statistics, which one would you want if the true population parameter is 5? So if we're trying to predict 5, this one right here is the best. Both 1 and 2 are predicting 5, but this one has lower variability than statistic 1, so it's better. This guy's biased because it's predicting about 6. It's not the right number. Okay, now, not all statistics make good predictions. Means and proportions are unbiased estimates. So if you look down here, means do a good job because the mean of X bar is always equal to the mean of the population. And mean of P hat, the sampling distribution proportion, is also equal to that mean of proportion. Okay, but standard deviation and range are awful. Okay, so for example, here's those original ones from the beginning. The population range is 40. That's the number we're trying to predict. But if I do sample range for all the different possible samples, notice that it predicts a sample range of 30. The mean of the sample ranges is 30. That is not equal to the population range. We have systematically underestimated the range. So this is what bias looks like. Standard deviation, range, almost all measures of spread are by definition biased statistics. They do not do a good job of overall predicting with their sampling distributions, but means and proportions are great. All right, so that is it. I'm going to stop talking. You have a worksheet you're going to do. If you have questions, let me know, and I'm here for questions.